Creatine converts to creatinine in acidic conditions. This is established chemistry. The rate of that conversion in the human stomach, under the conditions of normal digestion and typical supplementation doses, is approximately 1 to 2% per gastric transit event. That number is the core of the problem for buffered creatine's entire value proposition. Buffered creatine products, Crealkaline being the best known, but several others existing under different brand names, add alkaline compounds to creatine monohydrate to raise the pH of the product. The premise is that a higher pH creatine will resist acid-catalyzed conversion to creatinine more effectively than standard monohydrate, delivering more intact creatine to the bloodstream and ultimately to muscle tissue. The chemistry of the buffering premise is accurate in a laboratory context. Creatine stability does improve at higher pH values. In solution at neutral or basic pH, creatine can be stored without significant creatinine accumulation. In the research literature on creatine stability in solution, this pH dependence is well characterized. The clinical translation is where the argument breaks down. The stomach is not a static, controllable pH environment. It is a dynamic system with substantial acid-generating capacity, designed specifically to denature proteins and sterilize ingested material. Gastric acid secretion rates and the buffering capacity of existing stomach contents are multiple orders of magnitude greater than the alkaline content of a supplement capsule or tablet. The buffering agent in a creatine dose is neutralized rapidly by existing gastric acid. The creatine then encounters a pH environment similar to what it would face in an unbuffered form. The 1 to 2% gastric conversion figure, derived from kinetic modeling of creatine stability at gastric pH values with typical transit times I, establishes the ceiling for how much benefit a buffered form could theoretically provide. Even perfect buffering would recover that 1 to 2% of the dose. For a 3-gram supplementation dose, that is 30 to 60 milligrams of creatine, a quantity with no meaningful physiological significance. Head-to-head clinical trials comparing buffered creatine to monohydrate have not found the performance or muscle loading advantage the buffering premise predicts. Muscle phosphocreatine levels after several weeks of supplementation are not significantly different between the forms. Blood creatinine levels, which would be expected to be lower if less creatine were converting to creatinine tests, are not consistently lower with buffered forms. The cost premium for buffered creatine products is substantial. Products carrying the buffered creatine claim are typically 3 to 5 times more expensive per creatine gram than monohydrate. Given that the buffering premise addresses a loss that amounts to 1 to 2% of the dose, even before accounting for whether the buffering actually achieves its goal in the stomach, the cost-to-benefit ratio of buffered creatine cannot be justified by the evidence. The chemistry of creatine cyclisation is worth understanding in enough detail to evaluate the buffering premise properly. Creatine spontaneously undergoes intramolecular cyclisation. The guanidinium group attacks the carboxyl group, releasing water and forming creatinine, a 5-membered ring compound. This reaction is reversible but thermodynamically favors creatinine at lower pH values, meaning the equilibrium position in acidic conditions sits further toward creatinine. The rate constant for this cyclisation at pH 2I, the lower end of typical fasted gastric pH I, is approximately 100 times faster than at pH 7. This sounds alarming until you consider the transit time. Liquids in small doses typically clear the stomach in 30 to 60 minutes. At pH 2 for 60 minutes, the cyclisation calculation produces a loss of approximately 1 to 2% of the dose. At pH 4, the upper range of typical fasted gastric pH, the rate is substantially slower and losses over 60 minutes are less than 0.5%. To meaningfully change the creatine conversion rate in the stomach, you would need to change the stomach pH substantially, from 2 to at least 5 or 6. Achieving that with a supplement capsule would require a buffer quantity far exceeding what any practical supplement dose contains, and would also interfere with the stomach's digestive functions. The gastric environment has regulatory mechanisms that defend its acid content. A small alkaline addition is neutralized. It does not change the environment. Buffered creatine is a product built on a mechanistically reasonable but quantitatively insignificant premise. The chemistry is real. The magnitude of the benefit it addresses is not. That distinction is the entire argument.